Today's lesson is called Classifying Real Numbers. So we want to start out by looking at a diagram that gives you a basic idea of how these number systems fit together. So the diagram you see below is called a stack of funnels. It helps us classify any given real number easily. But first, we have to make sure we can describe what kinds of elements are included in each one of these groups or sets of numbers. Each group or set of numbers is represented by a funnel. So you're going to notice at the top we have the natural numbers. Next to that, I would like you to please write counting. The natural numbers are also known as the counting numbers. That funnels into the whole numbers, which funnels into the integers, which funnels into the rational numbers and ends in the real number bucket below. Then you also have the irrational numbers, which you can kind of see is off to the side, not funneling in with the others that you see on the left, but still ultimately ending in the real number bin. So what I want to do now is go through each set that we have and what the elements in that set look like. So we'll start with the natural numbers, which we just discussed is also known as the counting numbers. So counting numbers are exactly what you learned to count with when you were little. You started counting with the numbers 1, 2, 3, and so on. So those are the numbers we're referring to when we talk about natural numbers. Now, as an algebra student, you're going to start to hear things about set notation. And so when we write things in set notation, we start with a pair of brackets, and I like to use the technical term squiggly brackets when we're writing a set. So I would start with the bracket. I would list the first few numbers of the set, 1, 2, 3. Now you would need to at least list 3 of them because the pattern has to be recognized, but I would even suggest you go a couple more. And then the and so on that you see written here refers to the fact that it's going to continue to follow that pattern. So we will put a comma and then an ellipsis of 3 dots to show the continuation and then end our set. Next, we have the whole numbers. Now, we like to think of this as a very slight upgrade. So I will highlight that there, a very slight upgrade. And by slight upgrade, we mean we're just going to take the natural numbers that we just discussed, or counting numbers, and the only thing we're going to add to that is 0. So we add the element 0 to our current set of natural numbers. So think of it as the whole numbers are really just the natural numbers together with 0. So in our set notation, we will have our squiggly brackets. We will start with 0 this time, then 1, 2, 3, 4, and so on to end our set. So if you notice, we're getting gradually bigger. The natural numbers or counting numbers are smallest, just like in the funnel picture. Add just one element, we get the next biggest one, which is whole numbers. Now we're going to move on to the integers. So for the integers, what happens is we end up with, let me switch colors here for you so you can see a little bit better. We end up with all the whole numbers together with the negatives, or what I like to call opposites. Okay, so next to this, I'd like you to put a little arrow and also put that we could call this opposites. All right, so if we take the natural and whole numbers that we already had, and now we add the whole numbers opposites, we end up with the integers. So we're going to start actually with 0 in the middle, 1, 2, and 3, and so on, which are our whole numbers from above. Now we're going to add in the opposites of the natural numbers, or the negatives of those numbers. So that would be -1, -2, and -3. And then we'll put our ellipsis in front with our set notation. The next largest set is the rational numbers. Right in the word rational, we have the word ratio. So these are numbers that can be expressed as a ratio of integers. This means if we can write a number given as a fraction, where the numerator and the denominator are both integers, we end up with a rational number. So a couple things about this. We have to be careful of one special situation where it says caution here. We have to remember that the denominator can never be equal to 0. So you are not going to have 0 in the bottom of the fraction. And I like to explain this as how you learned fractions in the first place. When you learned fractions, you learned that the number on the bottom was the total number of pieces. So if we were talking about a pizza and we had 0 in the numerator, is it possible to eat 0 out of 8 pieces of pizza? Of course, you can choose not to have any slices, although I definitely wouldn't. But does it make sense to have 8 over 0? Can you eat 8 out of 0 pieces? Absolutely not. So remember, 0 cannot be on the bottom. Symbolically, the way we're going to write this is squiggly bracket, and then we can't really list like we did above because there are so many different combinations that we could have here. So what we do instead is we write A over B to show what a fraction looks like, and we describe the circumstances. So where A and B are integers, but B cannot equal 0. So discussing what we talked about before. So I'm telling them how to set it up as long as they put an integer in A and B's spot, but remember that B can't be 0. Now, special note underneath, rational numbers can also appear in decimal form. So we have rational numbers written as a fraction, as a decimal, but it's very important you understand the characteristics of that decimal. The decimal number has to either terminate or repeat. As long as that's happening, it is possible to write it as a fraction with an integer numerator and denominator, which therefore makes it rational as well. Then if you remember from the front diagram, we had the irrational bucket that was not part of the funneling happening on the one side, but was separated, still going into the real numbers, but in no relationship to the other number systems. And that one is called the irrational numbers. So for the irrational numbers, we are talking about numbers when they are in decimal form, they do not repeat, and they do not terminate. Or in other words, they can't be written as a fraction. So one example that is your most classic example of an irrational number is actually pi. We know that that decimal goes on and on forever with no repeating pattern. We have numbers that are the square roots of non-perfect squares, like the square root of 2. We know the square root of 4 is 2. 4 is a perfect square. That is not an irrational number. 2 is not a perfect square. So when we go to take the square root of it, we're going to get a decimal that does not repeat and does not terminate. And if you want to check that out a little bit closer, you can go to your graphing calculator right now, type in the square root of 2, and see the kind of number you get. Now remember, your calculator display will only show you so many digits. So it is important that you understand that and have a general understanding of those types of numbers. You could also see the number written like this, although we do not prefer it. You might see an example where you have a bunch of different numbers. And you're going to notice they're very random. There's no pattern, and you might see something like a dot, dot, dot at the end to show you that that random pattern is going to continue to happen. And then lastly, we have what holds everything together, the real number systems. This includes both rational and irrational numbers. So if we go back and take a look, remember right here at this spot, these two buckets still empty directly into the real numbers, even though the irrational numbers have nothing to do with the other side. So lastly, our real numbers are going to have all rational and real numbers, or rational and irrational numbers, sorry. And remember that under the rational number, we have the subcategories of integers, whole numbers, and natural numbers, as we saw early. The last type of number we're going to mention today is one that you will not deal with until you're in high school, but we do want to let you know that it does exist. And this is called an imaginary number. And that includes the set of numbers whose square is negative. So for example, we would have the square root of negative 100. Now here's the problem with the square root of a negative. We know when we learned integer rules that a positive times a positive is a positive, and a negative times a negative is a positive. And the definition of square root means I should be able to take a number and times it by itself to get the number underneath. There is no number times itself that's going to give you negative 100. At this time, go grab your graphing calculator and see what happens when you try to take the square root of negative 100. You are going to get an error message. At this time, I'd like you to pause the video and try the practice questions that follow, and then when you are ready, you're going to resume the video to check your answers. Okay, you've had time to do the practice problems, so we're now going to go over the answers to this. The first one says any integer is a whole number. This should be false. Now, when it's false, it's good next to it to put down an example of why you're choosing false. So for example, an integer is a whole number. I can give you an example that will contradict that. Negative 2 is an integer, but not a whole number. Right? If you look back at your list, negatives are not included in the whole numbers. Number 2, every rational number is also an integer. This is also false. Again, when you're trying to determine true-false questions like this, see if you can find the one exception. And most of the time, there's more than one exception. So here, think of a rational number that you know is not an integer. Well, 1/2 is an example of that. 1/2 is a rational number, but it's definitely not an integer. This one is one that hangs people up quite a bit. So if you go back and take a look, integers have negatives, but they don't have any fractions or decimals yet. We do not get fractions and decimals until we get to the rational numbers. Every whole number is a natural number. This is, again, false. All I have to do is think of an example that will throw this off. My example is 0. The whole number, 0, is not a natural number. Remember, natural numbers and counting numbers are the same. So when we learned to count, we didn't start with 0, we started with 1. Okay, they want us to classify the number 0. So 0, we want to list all the classifications for. We know it's a whole number. We also know that that's included as an integer. 0 can be written as a fraction, 0/1, so we know it is rational. And it's part of the real number system. Negative 2 1/5. That is going to be rational and real. We do not have any negatives in the counting or whole numbers. And we don't have any fractions as part of the integers. So rational is the first qualification that we have. Classify the number negative square root of 16. Now, this is not the same as when the negative is underneath the square root. This is the same as negative, and then the square root of 16 is 4. So that's really just negative 4, which means it's an integer, rational, and real. And then lastly, we have the square root of 20. 20 is not a perfect square, so that makes this number irrational. Now, I want us to write down the options we have in order to explain this. First option, it is a non-terminating. Remember, terminate means to end, so it's non-terminating, means it doesn't end. It's also non-repeating. That's important because if we have a repeating decimal, it's not irrational anymore, it's rational. So you can use that explanation, or you can talk about the fact that it is a square root of a non-perfect square. And that concludes your lesson on classifying real numbers.